All right, today we're going to pull back the curtain on the invisible science that runs pretty much everything. We're talking about the hidden rules that decide why some things bend and other things just break. It's a question that's playing out all around us, all the time.
I mean, really think about it for a second. Why can you stretch a rubber band like crazy, but a steel rod seems totally unmovable? A huge suspension bridge is actually designed to flex and sway in the wind, but a simple piece of chalk, it'll snap if you just look at it wrong. So, what is really going on here? Well, the answer is way more elegant and powerful than you might think. To really understand why things break, we first have to ask the opposite question. Why do they hold together in the first place? The secret is buried deep inside the materials themselves, and it's all about how they respond to forces. It all starts with two key ideas.
Okay, so the behavior of pretty much any material you can think of, it all comes down to this fundamental relationship between two concepts, stress and strain. Just think of them as a scientific cause and effect. One happens, and it makes the other happen. First up is stress. Okay, imagine you press your hand flat on a table. The force is all spread out, right? No big deal. Now, imagine that exact same force is concentrated on the tiny, tiny point of a high heel. Whoa, that massive concentration of force on such a small area creates way higher stress. It's why a sharp knife cuts so well, and it's why those heels can actually dent a wooden floor. Stress is that internal pressure a material feels. So, when a material feels that internal stress, it has to react. And that reaction is what we call strain. It's the physical change, the deformation that we can actually see. The stretch, the squish, or the bend. It's basically just a ratio of how much the shape changed compared to how it started.
So, this is the crucial part. The one rule you have to remember. Stress is the cause, and strain is the effect. Simple as that. You apply a force that creates stress inside the material, and because of that stress, the material deforms, which is the strain. This little cause and effect relationship explains literally everything else we're about to talk about.
Okay, so this leads us to something really cool. Most solid things have a kind of memory of their original shape. They can take a certain amount of stress and then just bounce right back like nothing happened. This amazing property is called elasticity, and it follows a really predictable rule. It's known as Hooke's law, and it's beautifully simple. You apply a force, that creates stress. The object deforms a little, showing strain. And here's the key, as long as you stay within its special limit, the second you remove that force, poof, the stress is gone and the object snaps right back to its original shape. Just think about gently bending a plastic ruler. It always comes back. But everything has its limit, right? That special point is called the elastic limit. It's the absolute maximum stress a material can handle before it's permanently changed. If you apply a stress that goes beyond this limit, it will not return to its original shape. The damage is done. Bend that ruler just a little too far, and it's going to be bent forever. And this brings us to a really fascinating idea. Every single material has its own unique personality. Seriously, the way it responds to stress is a core part of its identity, and that defines everything about it, from how stiff it is to how strong it is. Just take stiffness, for example. Scientists have a fancy name for it, Young's modulus. Steel has a super high modulus. It takes an absolutely enormous amount of stress to get even a tiny little bit of strain. But rubber? It's the total opposite. It has a very low modulus. A tiny bit of stress gives you a huge amount of strain. Two completely different personalities. So how can we actually watch this whole journey? From a material being perfectly fine to, total failure. Engineers have this incredible tool called a stress-strain curve. And you can really think of it as the complete life story of a material, showing us exactly how it behaves as we slowly crank up the force. This one graph tells the whole story. In the first part, the elastic region, everything's great. The material is just following Hooke's law, stretching and returning perfectly. Then, wham, it hits the yield point. That's the elastic limit we were talking about, where the permanent damage starts. If you keep pushing past that, the material will eventually reach its breaking point, and it fractures completely. Game over. Now, the way a material fails after it passes that yield point, that really tells you everything about its core personality. Generally, materials fall into two main camps. You've got ductile materials, which give you a warning, and then you have brittle materials, which give you nothing. Ductile materials, like copper or steel, are real troopers. After they pass their elastic limit, they stretch into form a lot, giving you this really obvious visual warning that, hey, failure is coming.
Brittle materials, like glass or chalk, do the exact opposite. They show almost no deformation at all. They just snap, suddenly, catastrophically, and with absolutely zero warning.
So, okay, why does any of this matter? Because understanding these personalities, ductile, brittle, stiff, flexible, is precisely how we engineer our entire modern world, from the biggest skyscrapers down to the tiniest little microchips.
This is where the science becomes real-world design. Suspension bridges use that ductile steel so they can bend and flex with the load of traffic and wind. The shock absorbers in your car are all about harnessing elasticity to store and release energy, making the ride smooth. And, so importantly, earthquake-resistant buildings are designed to be flexible, to sway with the force, instead of just rigidly fighting it until they shatter. And this really reveals the most important lesson in engineering, maybe in life. Pure strength just isn't enough. The best, most reliable materials are the ones that combine strength with flexibility. In a lot of situations, being totally rigid is actually a huge weakness. So I'll leave you with this thought. Our world isn't actually designed to be unbreakable. It's engineered to bend, to deform, and to absorb stress in a safe way. Which really makes you wonder, what does it truly mean to be strong? Is it the ability to never, ever bend? Or is it the wisdom to know exactly when you have to?